Okay, everybody, so we're gonna practice our curve sketching with this logarithmic function right here. Okay, so f of x is equal to the natural log of 1 plus x squared. So first of all, let's look at properties of this that aren't related to derivatives right off the bat here. So let's take a look, for example, at the domain. Okay, now remember how domain works with a logarithmic function here. Let me maybe zoom out just a little bit here, give myself a little bit more room. I can only take the log of a positive value. So I need 1 plus x squared to be greater than 0, which means I need x squared to be greater than negative 1. Now the truth is, that's always going to be true. Okay, because anytime I square a number, it's going to be greater than, it's going to be positive, so it's going to be greater than negative 1. So therefore, this is going to be true for all reals. The domain for this function will be all reals. Okay, let's take a quick look at the intercepts. Let's start off with the, let's say the y-intercept. Y-intercept is usually the easy one, so that's going to be y is equal to the natural log, okay, of 1 plus 0 squared. Well, okay, that is just going to be the natural log of 1, which is just going to be 0. Okay, so that's easy to find. I like that. Now let's try the x-intercept. I'm going to let y go to 0. So y is equal to, 0 is equal to the natural log of 1 plus x squared. Now, the base of the logarithm here is e, so this becomes e to the 0 is equal to 1 plus x squared. Because this essentially becomes a logarithmic equation. Okay, and to solve a logarithmic equation, I want to get rid of the logarithm, and I do that by converting forms there. And just bear in mind that if it's the natural logarithm, the base is going to be e. Now, e to the 0, though, is just 1. So that's 1 plus x squared. Cancel the 1's from both sides. I'm going to get 0 is equal to x squared. So x is equal to 0. So there's my x-intercept here. So my y-intercept is 0, my x-intercept is 0. So really what I'm looking at here is the point 0, 0. Okay, now let's take a quick look at the next thing I want to concern myself with here. Actually, I'll do it up here. 1, 2, 3, asymptotes. Okay. Asymptotes. Well, the asymptote occurs, if you think about just your regular natural log of a function, the asymptote occurs at where the argument goes to 0. So essentially, this would be where 1 plus x squared is equal to 0. And the truth is, x squared, that would require x squared to be equal to negative 1. And there is no real number that does this. Okay? There's no real root here. So there's no asymptote. Okay, at least not in the system that we're working with. So anyway, we can just move on from there. Now we're going to take a look at where the function itself is positive or negative. Okay, I want to know where f of x is going to be greater than 0 or less than 0 here. Not that this is 100% necessary to graph these things, but it gives us a sense of what's going on. Now, I want you to think about that. If you think back to what a regular logarithmic function looks like, okay, y equals the log base b of x. It goes greater than 0. It jumps above the x-axis here when x is equal to 1. So as long as x is greater than 1, the logarithmic function here is positive. So to start off with here, considering that I'm taking the natural log of 1 plus x squared, really what I'm interested in is where what's inside the log is greater than 1 here, or 1 or more here. So let's say I'm interested in where 1 plus x squared is greater than 1. Okay? No, not or equal to. Okay, not or equal to, but just greater than 1 here. So subtract the 1 from both sides here, and I'm interested in where x squared is greater than 0. And the truth is, that's going to be true as long as x doesn't equal 0. So this is true for all values of x except 0, that this thing is going to be above the x-axis. Okay? And when x equals 0, I know that the function is going to equal 0. So there's nowhere where this function is actually less than 0. So it's always positive or 0. So x is not greater than 0. And this implies that f of x will be greater than 0. Okay, that's where that's true. Okay, good. Now we've kind of dealt with all of that here. Let's get on to the derivative here. So that was 4. Let's go to 5. So in 5, we're going to take a look at the first derivative. We're going to look for critical numbers, min-max values, where the function's increasing and decreasing. So we'll just rewrite the original function because it's nice to have that handy as we're going through this. The derivative will be 1 over 1 plus x squared. And then I'm going to multiply by the derivative of what's inside there, okay, using the chain rule. I'll just do that right on top here. And that is going to get me 2x. Okay, so the derivative of the natural log of 1 plus x squared is going to be 2x over 1 plus x squared. Good. So now I am interested in determining the critical numbers for this. The critical numbers occur in the domain of the function where the function is either undefined or equal to 0. Now, we've already looked at this. We already know that the domain is all reals. Okay. So if we look at where this thing would be undefined, where the denominator goes to 0, it turns out it never does go to 0. Okay? Any value of x that you throw in here is either going to be 0 or greater, and if you add that to 1, you're never going to get a value of 0 in the denominator. So, okay, so that's good. So now we're just interested in where the first derivative goes to 0. That's only going to come out of the numerator, and that's going to be where x is equal to 0. So along our number line here, what we've got is we've got 0, and that's our critical number. Okay, x equal to 0 is our critical number. Let's check the intervals of increasing and decreasing. If we choose a value to the left of 0 and plug that in, the denominator is going to become positive and the numerator will be negative. So the function will be negative here, so it means it's decreasing. Over here, if you chuck a positive value in for x, oops, okay, this will become positive over here. That means our function's increasing. Okay. Oh, sorry, you can't hardly see that. Now, let's talk about this. This function is increasing on the interval. Now, when I do this, I include the 0 in this. So this is going to be increasing on 0 out to infinity. Now, I know some people aren't going to do that. But there is a difference between the interval where the function is where the derivative is positive and where the function is increasing. And that's because increasing is defined by comparing 2 points. And as long as the 2 points have different x values and the y value of the one is greater than the y value of the other, it's increasing. So I'm going to include those endpoints there. It's increasing on that closed interval. Okay, and vice versa, if it's below, then it's decreasing. So when I see that my derivative is positive on this open interval greater than 0, I conclude that the function is going to be increasing on the half-closed interval from 0 to infinity. It will therefore be decreasing on negative infinity out to 0. And notice I'm including the 0 in that interval as well. That communicates something to me. If a value is like the end point or the beginning point of an increasing sequence and the end point of a decreasing sequence, decrease, increase, that means therefore I have a min at the point 0, and we've already established this, 0, 0. Okay? I've got a minimum happening there. It is the end point of a decreasing sequence and the beginning point of an increasing sequence. It has to be a minimum. Now, in this particular case, I can go one step further here. I know that this is going to be this minimum value, this local minimum value, but it's also going to be an absolute minimum because it's the only minimum I get. The function prior to 0 is always decreasing, after it's always increasing, so I can go even further. This is going to be an absolute minimum value there. Okay, let's go one step further. And obviously the step beyond this is going to be to take the second derivative. Okay, and we'll take a look at concavity and whatnot there. So first of all, our first derivative was this expression right here. I'm going to require the quotient rule to take the derivative of that. So the derivative of the numerator is 2 times 1 plus x squared minus the numerator multiplied by the derivative of the denominator, which will be 2x, all over 1 plus x squared squared. Okay, now let's just simplify that. So I would distribute that through. So 2 plus 2x squared minus 4x squared all over 1 plus x squared squared. So what have I got here? I've got negative 2x squared. Sorry, is that on the screen? Yeah. Negative 2x squared plus 2 over 1 plus x squared squared. Okay, well I could factor out a 2 there or a negative 2 there, but it's really not going to change much here. Let's talk about points of inflection or cusps. So those are going to occur in the domain of the function. We already know that the domain of the function, this is going to be all reals, where the denominator goes to 0 or the numerator goes to 0. Now, when the denominator goes to 0, the second derivative would be undefined, but that's not going to happen here. Same reason as it didn't happen for the first derivative. So I'm not really worried about that. What I'm worried about here is where the numerator goes to 0. Okay, where negative 2x squared plus 2 is equal to 0. Well, bring that 2x squared over, and I'm going to get 2 is equal to, positive 2x squared, cancel that out. Oh, okay, I'm going to get a couple values here. Plus or minus 1 equals x. Okay, there we go. So now, what does that look like here on the number line? So this is going to be negative 1, positive 1. Okay. Now, if I choose a value less than negative 1, now I already know that this is going to become positive, so that's not a problem. If I choose a value, let's say like negative 10. Negative 10 squared is going to be positive 100. It's going to be negative 200 plus 2. Okay, that's going to be concave down. And I like to do it like this. See, look at that. Negative, so sad. And actually, because there's a little bit of symmetry over here, okay, if I plug in positive 10 into this squared, that's still going to be negative 200. So it's going to be negative over here. And if you plug in 0, because I'm lazy and 0 is easy to plug in, if I plug in 0, that goes to 0, that term goes to 0, and so I'm going to be left with a positive. So that means that this function here is going to be concave down on the interval negative infinity to negative 1, and I'm going to include that, union 1 out to a positive infinity, and it'll be concave up on the interval negative 1 out to 1. And notice I'm using these closed interval here because I know that if a number here is part of both of those intervals, that it's got to be a point of inflection. See, if I use open brackets there and I don't include it, then I'm not entirely sure whether that's the point of inflection or whether that's supposed to be an asymptote and it's not even in the function. I don't know. But this one's pretty clear to me. So I've got now 2 points of inflection. My points of inflection are going to be at the point where x is equal to negative 1 or positive 1. Now I just got to go back up to the original function and figure out what that is. Way up here. So if I plug negative 1 in, it's going to be 1 plus 1, so the natural log of 2. And if you plug positive 1 in, the same thing. So both cases here, I'm going to get 2 and 2. All right, so now the last thing I'm going to do here is sketch this thing. Okay, I know that there is a key point here at 0, 0. I also know that there's a key point here at 1, let's say 2, and at negative 1, negative 2. Those are important points here. Now, along the top here, I'm going to identify the intervals where this thing is increasing and decreasing, and the only change that I get there is that it's decreasing to the left of 0, increasing to the right of 0. In terms of my concavity, I'm just going to draw a little number line down here. My concavity changes at negative 1 and 1. It was concave down here, up here, down here. So, what is happening? Well, okay, to the left of negative 1, this thing is decreasing and concave down. So that's going to look like this. Then it's decreasing and concave up, so it's going to look like this. I've already established that this is going to be a min, so this thing's going to drop down, level out, pass through it, come back up. Okay, it looks better on the right than it does on the left here. Hold on. Maybe come out from there. That's better. So I can see that the concavity changed there. Now my diagram's a little off here, but you get the idea. Comes down, concave up, hits here, now changes to concave down, but it's still increasing, so it's going to look like this. And there you go. That's what the graph's going to look like. Now that's a little exaggerated. If you go to your calculator, it won't look like that. But that gives you a really good sense of what's happening on that particular graph.